Welcome to this video on computer-aided modeling. Here we will show you the step-by-step model development with MOT. We will use a simple example to highlight the modeling steps. In order to develop a model, various modeling steps are needed, and some of these can be accommodated with modeling tools also to help with the modeling. For example, representation of the system in terms of equations or symbols, guiding principles for deriving the model, like conservation principles. The model usually will have parameters, so regression of parameters with different types of tools can be done. Then analysis of the model. Is it well defined? What are the degrees of freedom? Which variables to specify? What kind of solvers would be needed? And then identifying the solver that is needed, connecting it with the solver, and setting up the call to the solver and solving the equations, and then analyzing the results, representing the results in figures, and so on. If all those tools are combined together in a computer-aided modeling system, then significant reduction of computing time or development time of the model can be achieved. And this is done by combination of parts or modeling steps that the human can do very efficiently and reliably, and the computer can do very, very fast and reliably. So a perfect combination is needed to develop the models in record time or very fast. And once the model is developed, the model can be saved and then exported to other systems that can use the model for simulation, optimization, and so on. The model can be stored in a library for future reuse, and the model can be used to develop other systems for synthesis, design, control, analysis, and so on. And the individual systems can be combined to form integrated systems. The model that will be developed needs a system. So the system description in this example is a simple system where a spherical particle settles in a fluid under the action of Earth's gravitational acceleration. This mathematical model deals with unsteady state free settling of a particle in Stokes law region. The mathematical model is derived from a momentum balance on the system. So the mathematical model could be classified as a lumped parameter model, dynamic model. The first equation is ordinary differential dynamic equation or ordinary differential equation, and the rest are algebraic equations, some of which are classified as constitutive equations, and the last two are classified as defined equations. So these equations, that is a ordinary differential equation plus algebraic equations, now need to be solved. So that is our model, and we will solve it. And the example will highlight the different steps of importing or exporting these equations into MOT, and then MOT will import the equations, translate the equations, solve the equations, and so on. So the starting point is a mathematical model that is already available. MOT will translate, analyze, solve, and create the model objective without the user having to write any programming code. The recorded video will highlight the steps in green and will start with a short introduction of MOT. So model construction will include importing the model and translating the model in MOT. Then it will analyze the model, then the model solution steps will be highlighted, and then the model verification results and model objective will be highlighted. So enjoy the rest of this recorded video in 5 short steps. Thank you very much.
Welcome to this beginner's tutorial on how to use MOT. MOT is an equation-based simulation tool consisting of algebraic solvers, numerical integrators, and an optimizer. And it's capable of solving any kind of process system as long as you have the model equations. In this series of tutorials, you will learn how to use the basic functions of MOT by solving a simple model. First, I'll walk you through creating your own model, analyzing the model, solving it, and then saving the data. For more in-depth explanations of the features of MOT, you can always look in the MOT manual. First, we need to open MOT. We do this by double-clicking the executable. Now in this window, we choose MOT. And for this tutorial, we will not be using workflows, so choose Do Not Use Workflows. Now MOT is open and we're ready to start creating our model. In the next video, 102, I'll walk you through the steps of creating your first model. Hi, in this tutorial, I'll show you how to create your first model in MOT. We start by going to the Definitions tab here, and then we go to View Original Model. Now here you can see that there's currently no model present in MOT because we have to create it. So we go to Create Model, and here we can manually enter all the equations we want to use. For instance, I can type F equals M times A. Now this is an equation. If I put a hashtag before any text, it'll be a comment. Like this. Once I've written all my equations, I have to go to this button up here that says Accept Changes and click it. Now for this tutorial, we will not be using compounds, so I'll select compounds not used in this model, but there will be a YouTube video available showing you how to use this feature. For now, just select this and click OK. Now MOT is showing us the translated model with all our equations. Notice that the comments aren't available here. If you want to view the comments that you wrote with the equations, we go back to View Original Model. Now the actual model we want to solve in this tutorial is a bit different. So to enter the right equations, we now go to Modify Model, and we can delete these initial equations here. And you can find the equations you need in the MOT manual, which I have open here. And you can just copy and paste the equations into the window. So what this model is, it's basically a spherical particle that's settling in a liquid under the gravitational effects of Earth. And here we have an algebraic equation for the mass, the weight, the buoyancy force, the Reynolds number, the drag coefficient, and the drag forces affecting the particle. And we'll be solving this differential equation here with a momentum balance on the particle and calculate its velocities during a period of time. You can see that the D here in front of the U denotes that it's an ordinary differential equation. Once you've copy-pasted the equations into the Modify Model window, we again go to Accept Changes here. Now MOT is showing us a translated preview of the model, which we can just accept. And again, we will not be using compounds. And finally, when you modify your model in MOT, it will tell you if any variables have been removed from the previous model. In this case, there's no longer a variable called A or F in the model, and therefore MOT is just letting us know. So now I can just click OK. And again, you can now see the translate model here, and now you've created your first model. In the next video, 103, we'll then proceed to classify the variables so we can solve this model. Hi, in this tutorial we will now analyze the model we've created and set up all the variables so we can solve the system. In MOT, it will automatically identify all the explicit variables when you create your model, and the rest of the variables will be set to parameters by default. It is then up to the user to define these variables so they're listed correctly. To do this, we go to the Definitions tab, and then we go to Classify Variables. Now here we can see all our variables in the Classify Variables area, and they're all currently set to parameters. Over here we can see the explicit variables that have been detected by MOT, and their current value, which is 0 because we have not yet solved the system. Finally, we have this incidence matrix over here. We can zoom in a bit, and this shows the relationship between the equations and the variables. For this model in particular, our diameter, densities, and viscosity will be specific values for a specific fluid or particle and will be known. Gravity is a constant and will be a parameter. And finally, U is our dependent variable. Now notice how, as we classified the variables, the colors here in the instance matrix has changed a bit. The green colors here is the known variables, parameter is the dark blue and our dependent variable is the light blue. You can look in the manual and find a better, more broad description of the color coding used in this system. Once we've classified all our variables, we then need to relate our dependent variable to its dependent prime. In this case, relate u to du. To do this, we go to relate dy dt to y here. Now we see that our dependent variable u is here, and we'll find the dependent prime from this drop-down menu, du here. There we go. And now if we go back to classify variables, we'll see that du has also changed color here to a light blue. Finally, before we solve the system, we have to set the values for our known variables and the parameter. To do this, we go to set variable value here. Now we can manually enter the values for these variables. These can all be found in the MOT manual here on page, on page 27. I'm just going to type them in manually. 0.002 and 900 for density here, and 0.05 for the viscosity, and gravity is 9.81. There we go. Now we've set up all our variables and classified them, related them to each other, and set the values of our known variables. In the next tutorial, we'll then proceed with solving the system in video 104. Hello. In this tutorial, we will now solve the model that we built and analyzed in parts 102 and 103 in this series of tutorials. Here we're at the classify variable screen, where we can see that the variables have all been classified. At set variable value, we can see the values we set them to. First, we'll go to the solutions tab, which is located down here. Once we click this, we'll have a new set of options available. Let's start by going to the solver options. Here we can choose the options for the solver we're going to use when we solve the model. The most important thing right now is select solver, where we can see that there are 4 different solvers available. In this case, we'll just use solving via finite difference approximation, which is very good for solving algebraic problems. The rest of the options we'll leave for now. Next, we'll go to stepwise model solution. This is very useful for when you want to solve your equations one by one and just get an idea of the results that you're getting to make sure that they're reasonable or consistent. So to solve the equations one by one, we go to step solve model here and we'll click it one at a time. Now on the right, we'll see the values that are coming out. I won't discuss these values too much. In this case, we'll just say that they're fine, but in the future with your own model, you can use this to check if everything's running correctly before you solve the full model. Next up, we go to variable chart trace. Here we can decide which variables we want to plot. In this case, we'll be plotting them against the independent variable, which is time. To plot our variables, we first check this box here to allow the variable chart trace. Then from the drop-down menu here, we can choose which variable we want to plot. Since the model is describing a particle moving and going to rest, it'd be interesting to plot the velocity of the particle. This is what's depending on the time. Then we'll go to solve model. Now here we have 3 sets of options available. We have algebraic options, dynamic options, and optimizer options. This is a dynamic problem, so we'll use the dynamic options here, and we'll just leave them all at the default values. So we'll use the BDF dynamic solver and forward integration. Also note that there are 61 time steps with an end time of 1.0 when we solve the model. So to solve it, we'll just go to solve, and we'll now save our file as well. So we can call this MOT test, for instance. And we're saving it in the default MOT folder. And now MOT has finished solving the model. In the next video 105, we'll go through the results, and I'll show you how to view them and save them and store whatever data you need. Welcome. In this tutorial, we will look at the results from the previous videos and conclude this series of beginner's introduction to MOT. Now here we've just solved our model and we have a few windows open. This over here shows us the progress of the solver. This here shows us that the solution is complete and we can now view the results. And we've also got a plot hidden away here. We'll start by going through results to see what's happened. So we only had one dependent variable, and we can see the value before and after the solution. So it's gone from 0 to 0.3. We can also view the values of our other variables in our system if we click Show All Items. Here we can see all our constants have the same value, but some of the other equations here have changed the value over the course of the solution. Just close this for now. Before we click OK here, we want to check out our plot because that will close once we click OK. So our plot will be down here in one of the tabs. There it is. And this shows us the value of u as a function of the time. A few things you can do in this plot in MOT. If you hold down left click and you drag the mouse, you can zoom in on a specific section. You can also right click to zoom back out. Finally, if you want to save the data that this plot has been made with, we click Save Points Now, and we can then specify a path. So I'll just select the default MOT folder, and I choose which plot I want to save. If I had more variables I was plotting, I would have more options here, but in this case I'll just choose U. And then I'll have a prefix and a postfix in the file name. So I can call this again MOT test, for instance. And then underscore, because then the U will be here, this U, and then it'll be a CSV file. Then I click OK. Now if I find the MOT folder, see here MOT test underscore U, I've now saved the file as a CSV file, which I can open in Excel or other programs to then plot the data however I want. I could also just have clicked Save Points when done and close the window. And then it should also prompt me here to save the file. But in this case I just click cancel. Okay, now that we've saved the data and we've looked at our variables, we're ready to close down this window here. We just want to make sure we just check these two options first. So we can either choose to update unknown and time dependent variables, or we can leave them as they were. In this case we'll say update them and click OK. Also note that this here shows you a few statistics about the solution. That we have 7 equations, it's been solved about 1,100 times, time, and so on. Okay. Now if we go back to our definitions tab here and to class or set variable values, we can now see all the variables we found from the solution have been updated. Also, if we want to save the file again, we can go up here to File, Save As. I'll just overwrite this file here after we solved it. There we go. Now you have basically created, analyzed, and solved your first model using MOT. There are of course many more advanced features such as parameter estimation, sensitivity analysis, process optimization, and a lot more. And as time goes on, there will be videos available on YouTube describing how to use these features. So feel free to check them out and learn more. And of course, you can always look in the manual for more in-depth description of all the things I've covered in these tutorials if you need it. For now, thanks for watching and see you next time.